Welcome to one of Avail's first Whiteboard sessions. Today we have Bader from Polkadot joining us. He'll be talking to us about Polkadot, about the relay chain, Parachains, Substrate, interoperability, and then we'll also talk a bit about comparing Polkadot's relay chain, Parachain ecosystem with Ethereum's base layer and roll-up ecosystem and such. And so welcome, Bader.
Yeah, thank you so much. Really glad to be here. Hopefully get into some fun topics today with Polkadot and like scalability and kind of comparing and contrasting some things. But yeah, thank you guys.
Cool, Bader. If you can just start off with like a brief introduction of yourself in terms of how much time you spent at Polkadot, for example. So just to give the audience some color on where you're coming from.
Yeah, so I started actually with Ethereum smart contracts when I was like 17. Back in around 2018, 2019. And from there, I kind of discovered Substrate actually last year, where I built out this peer-to-peer messaging app using Substrate. From there, I also went through the Polkadot Blockchain Academy and got to really know the community, both physically and also virtually, and then eventually joined the Web3 Foundation around 6 months ago, where I work as on the education team at the Web3 Foundation.
Awesome. Okay, so I think maybe we'll just jump into the meat of it, right?
Sure.
Maybe, Bader, you can feel free to use this board. To maybe we can quickly get to the high level end-to-end architecture of the Polkadot relay chain but in general the whole ecosystem, and then we can get into each of these separately.
Right. So to kind of start off with, and first of all, my handwriting is terrible, so just. So Polkadot, and I'm going to use some words that are a little bit sound like buzzwordy or marketing-esque almost, but really it is, at the end of the day, it's a heterogeneous sharded blockchain. And what I mean by that is essentially it has this concept of the relay chain, where the relay chain kind of takes care of these core activities between various shards within the network, right? So you have like these shards here, or also referred to kind of as cores now, we're starting to see. And these various cores can actually hold, again, it's heterogeneous, meaning each shard or core holds a different application logic within. So you can have a completely separate blockchain or kind of state machine off of one of these cores, and at the end of the day, they will sync with the relay chain and be part of the relay chain state. So when you check like a relay chain block, the state root of that or the hash of that block will actually represent all these different parachains and cores together. So as you can imagine, this has a lot of use cases and a lot of good implications, especially for security and for trust, because now you're able to verify the state of many different sub-blockchains, which we call parachains, into one single, into one relay chain block. And this includes like finality, and of course there's a bunch of stuff with the parachain protocol, which verifies how parablocks, as we call them, are actually verified on the network. But yeah, in its essence, Polkadot is a blockchain that lets other blockchains talk, interact with each other, and achieve this kind of sense of shared security by having them participate in the relay chain's processes. And then, so as I kind of mentioned, right, we have these different parachains, and the core goal of Polkadot is to facilitate many different applications on the same blockchain. There's kind of this core belief that, many blockchains, as useful as they are, it's hard to have a general blockchain that does everything. So what Polkadot does instead is it says, here we offer you these slots, you can vote, you can auction off these slots and become a parachain, write your very application specific logic, be very good at what you do, while still being able to talk to other chains, which might be useful. For example, there's like identity parachains, right? They can offer a general identity solution, and then another parachain can use that identity solution if they need to, just as a very high level example. The things that secure the network are there's a nominated proof of stake system as far as consensus goes. So that's kind of helps with the economic security, right? And then we'll get a little more into that, I think, a little later. Another good couple things to note is that there's the block production. So block production and finality are actually kind of decoupled. This is so basically, this is important because then we're not really waiting on the network to finalize a block each and every time. And this uses something called grandpa finality. So in essence, basically each of these parachains can say to the relay chain, hey, I have these set of changes I want to execute, these various state transitions. Here's how they should be executed, and this is called the proof of validity function. So the PVF gets sent from each parachain to the relay chain to a subset of validators. So basically in each era, the relay chain selects at random a subset of validators, right? Obviously, if we knew which validators was going to be assigned to each parachain, you could easily kind of game that, and you can kind of, always say, hey, these always look correct. But in order to have it unbiased, you want it to be random. And this is actually it uses actually the randomness from the block production protocol to achieve that randomness. It has a sense of, actually it's called Babe. That's actually what the protocol is called. And it allows you to also have a source of randomness on chain, which is very useful based off of the history of the blockchain. So you have to wait for the blockchain to populate a bit. If you're like starting a development chain, then you'll get some sense of randomness on chain, which is useful for getting these validator subsets to verify the parachain.
Okay.
Yeah.
So basically, we are kind of, because at Avail we use Substrate, which is the blockchain development framework by Polkadot. So our chain also uses, the Avail chain also uses Grandpa Babe. So Babe for block production and Grandpa for finality in general. And we also use NPOS.
Okay, I see. Interesting. Yeah, and that's kind of the cool thing here is that because these parachains, you can basically, as long as they provide the PVF to the relay chain, you can kind of put whatever you want in terms of block production or consensus or runtime on your respective parachain.
Okay.
As long as it abides by this PVF. And basically with the PVF information that it needs, whenever it sends up the parablock, it needs to just know, of course, it contains the proposed block of here's the state transitions.
Yeah.
Here's, maybe I changed some balance of some account on parachain A, and I want to, make note of that on the relay chain. So it's able to send up those transitions, as well as just the path of the Merkle tree that represents that specific state change. So you're just verifying that part of the Merkle tree along with the PVF. So a balance is supposed to change X way on parachain A, and it verifies that state transition happened.
Okay. So basically, I'm just trying to understand this, right? Like, so what exactly is sent from the parachain to the relay chain? So this is like, I'm assuming the parachain does Grandpa Babe. So there's a justification on that is arrived at on the parachain. And what do you mean by PVF? Like, is there a justification and the state root the previous state root and the post state root? Like, can you just explain that in detail?
Yeah. So I think I should also go back a little bit and explain how parachains do this, because maybe you're asking, well, do parachains themselves have validators? Do they themselves run their own set? And there's this notion of something called, so here, let's actually create some new thing, some over here. Yeah, let's erase this. And let's actually start building out our parachain core and architecture right here. Yeah, perfect. But yeah, that's a very good question, because it's, what data is passed, and some people even get worried. It's like, are you just passing huge amounts of parachain state to the relay chain? Can't I just clog up that relay chain now? Mm-hmm. And the answer is really, you're just, here. So here we have our parachain, and then off of this parachain, we have these things called collators. Mm-hmm. And collators, you can think of them, they behave like a validator on a normal blockchain, but they don't really have to have any security guarantees. Mm-hmm. All they do is supply these candidates, this candidate information. It's candidate because we haven't verified it yet, to the relay chain's subset of validators.
Okay.
So this also supplies the PVF as well. So this also supplies our proof of validity function. Mm-hmm. And it's this function, right, that, each parachain mutates state in a different way. So how's the relay chain supposed to know if that was correct? So when it sends that block, it checks against the PVF. This is uploaded as like a blob of WebAssembly code, essentially. And that's executed against the proposed state of changes. So you have a block with X amount of changes in it. The PVF is basically ran against that. And if that checks out and also computes with the relay chain's final state root, as you said, a justification, of course, each amount of state is represented by a Merkle tree, including the parachain. So if the path, if these state changes match that state root of the parachain's like Merkle tree here, then we know that these are probably correct. And then we're able to send that as a proposed, like, hey, this looks correct. And that's kind of our first round of like validity checks that happen when we send up a parablock.
Okay. So just to get a mental picture correct, right? Like, so there are these X number of parachains, and
Yes.
like each parachain is doing a block. How do parachain what is the block production logic on the parachain? Is it like who runs the parachain in general?
That's a good question. So anyone can really, it's whoever, the parachain team, they run the parachain, they kind of can choose how blocks are produced, what blocks should look like. The only thing they need to do is make sure they implement this PVF, and it's really like a small bit of code in your Substrate code base that you implement and say, here's how my state transitions are supposed to look, translate them to whatever your parachain is doing. And actually, a fun fact is that your parachain doesn't really need to even be a blockchain necessarily. Like, it's possible that you only provide this PVF for whatever state changes you're making.
Okay.
You're generally just defining these finite state machines that sync to this bigger state machine.
Okay.
Right? It's like a bunch of distributed state machines that are syncing with each other and verifying the validity of their blocks with one another.
Okay, makes sense. So I'm assuming like something that, let's say, a parachain that runs an EVM will have a PVF that is associated with that state machine, for example. And so the complexity of the PVF may vary with what kind of parachain logic is there.
Yeah, exactly. It's worth noting that the PVF can, I think, get fairly large. I forgot the exact amount, but it can be fairly large because you're uploading essentially code. The nice thing is that Polkadot kind of uses WASM or WebAssembly as this general like a meta protocol, right?
Yeah.
That the whole ecosystem kind of speaks. So if I need to send you a way to prove that this block is legit, I send you the PVF, which is in WASM, which you can execute in some constrained environment to verify that this bit of computation is good to go.
Okay.
Yeah.
So I think basically where I have reached in trying to understand this is, so there's this parachain can be run by anyone, like mostly it's the team that runs it, for example, but typically it can be a smaller set of people who are running the parachain. Yeah. And there is a collator node which and there is a PVF that is specified by the parachain team.
Yes.
Which corresponds to the business logic or the app logic of the parachain.
Exactly.
And this is in WASM, and this is basically the data associated with the parachain transactions. So things like the updated state root, for example, and I'm assuming the transaction data as well.
Yeah, exactly. So naturally, at the end of the day, a transaction is merely just a state transition of some kind, right?
Yeah.
It modifies some sort of state.
Yeah.
The way that the state is interpreted obviously is dependent on the context. So in the context of the parachain, I might have some Internet of Things protocol, and I have a certain way of verifying that my devices belong to this network. They have to send some registering transaction that registers themselves to the network.
Yeah.
Of course, the relay chain doesn't know what that is, but that's why we need this proof of validity function, this PVF.
Yeah.
Because it's it allows us to say, hey, here's how it's supposed to look. And here's the Merkle tree, here's how the state root is supposed to look. Now compute it for me and ensure that what this collator sent is honest, right? And the cool thing about collators is that, again, they don't need security guarantees really, because at the end of the day, the relay chain verifies that through this PVF.
So the collator are more like relayers.
Basically, yeah. They just supply the data. They just supply the data. And let's say the collators are dishonest, right?
Yeah.
You need basically, you only basically need one honest collator in this whole setup.
Yeah.
Of course, parachains run different ones. And some parachains, diving more into that, some parachains choose to incentivize people to run more collators. That's up to them. Or they can run it themselves. It's really in their best interest to do so, because then they don't get the finality from the relay chain. So if you don't have a collator, it doesn't really benefit you to be a parachain at that point. So.
No, so I think this is, of course, not similar, but like there's a similar mechanic happening in Ethereum rollups today, where there's a sequencer that pushes the data to Ethereum. Typically in a rollup, sequencer will push the transaction data, some state metadata like state trees, for example, right? Roots, for example, and of course, depending upon whether it's a optimistic or ZK proof, it will provide the proof as well, right? So I think, and I'm assuming it passes the transaction raw data as well, correct? The collator, when it pushes the parachain block to
the relay chain.
So the transaction data and the state root data, is it?
Yeah, it includes like the partial path. I guess we're getting a little more technical, like a Merkle tree. The way if it's a proper one, I forgot what it's called exactly. Maybe like a Patricia Merkle tree or something. Yeah. I think that's what it is. You only need a partial path really, because the Merkle tree might be like very, very large. So if we have like, I don't know, I'm changing some like balance here, and this balance, let's see, just a random tree here, have like this, and then have my like state root, something like this. Let's say I only concerning myself with the balance, then I don't really need to worry too much about like this part of the tree. I can just verify this path or whatever and get to the state root, something like that at a very like high level. So we're not sitting and sorting through a massive amount of data.
Okay, so the path, the roots and basically the paths of the Merkle tree.
Yeah, exactly, of the parachain state.
Okay.
That way we actually can know that the data executed in the parachain is valid.
Got it. And so this is now very clear. So now I think we can move to the relay chain thing, right? Like what does the relay chain do when it receives the block?
Yeah, so that's a good question. So after it receives all that data, I'm going to just erase this for now. So after it receives that potential parablock, it's still, in this case, it's not validated yet. Yes, we've sent it. Yes, we have verified that the state transitions are correct, but the validators, or the subset of validators on this relay chain, still, need to actually verify this before it gets sent out to actually the wider set of validators. So you can see there's multiple levels to this, which is in the Parachains protocol. It's part of the Parachains protocol called these validity and proof checks, availability checks. Because we check first the availability of information as well as validity of information. So once we get this block, this parablock now becomes a candidate, right? This becomes a candidate block because it's a candidate now to be included in the relay chains network. And of course, when I say block, I really mean header. We're not including whole blocks of information in the relay chain. Yeah. We're including the headers of those. So, basically that state root or whatever that block represents. Let me see. But yeah, this also gets sent to these validators, where these subset of validators kind of agree on whether this block is also valid or not. And these, I'm trying to think of a way to explain it. These will also get it prepared to send it to the wider set of validators in the network, along with actually an erasure coding. So there's actually some data availability there, where you send the candidates blocks erasure code to all the other validators, so that when they come to consensus or achieve finality, they're able to also get the state of that exact parablock.
Mm-hmm. Okay. And so as we have now understood, right? Like, so basically the data that is sent from the parachain to the relay block is the Merkle root and the path, the relevant paths where the changes were made, and then these make their way to the relay chain. And does it do any more, I understand the part about making the data erasure coded, for example, right? But is this information enough to reconstruct the state of the parachain on the relay chain?
Oh, I see what you're saying. Like, is this state root here just a simple Merkle tree enough to do that? There's a series of other checks that also occur. They're not coming to my head immediately right now. There's more validity checks. There's like a second round even after the candidate block is done. The details are escaping my mind at the moment. That also ensure, but yeah, like the relay chain has its own set of checks that it does to ensure that this block is also valid. Yeah.
Okay. And the reason I'm asking is because like when we are building rollups on Ethereum or on Avail, for example, right? Like so, what rollups do generally is either they submit the entire transaction data, the raw transaction data, or like state diff data, and of course the pre-state root, post-state root, for example, right? Like, and so that allows us.
It does this very similar thing, especially in terms of like the post and previous state roots. It does a very similar thing to ensure that this data was changed correctly compared to the last time. So it does some similar things. The details, I'm like
no issues. So basically, so what you're saying is this data makes its way to the relay chain, and a subset of validators now. So the relay chain also has grandpa babe consensus, right? Like that's the same consensus mechanism, but the block production logic is different, obviously.
Yeah, of course, it's naturally a little different, and that's actually going to change soon, and we can get to that when we talk about scalability. But currently, you may say that it's like quite synchronous. The process of setting parablocks up, you have to wait for these changes to kind of stack up. Typically, parablock takes around, I believe, 6 seconds to validate, and a relay chain block. Sorry, the parablock takes 12 seconds to validate, and then the relay chain block takes around 6 seconds to validate.
Okay.
But that's because this process is quite synchronous. Eventually, the hope is to kind of have like this pipeline where these blocks are able to kind of get like built out asynchronously and then included onto the relay chain as they kind of need to. So you can like start as a candidate block, move to like a backable block, and I didn't mention backable, I think. A backable is what happens when the subset of validators validate. So now it's a backable block, right? And then it finally gets included when all the validators agree, and that's included and finalized. So yeah, the idea is like with asynchronous backing is that you can like kind of have this pipeline where things are being built asynchronously. So when they're ready to go into the network, they can just like jump into the network and be included. And that will cut it down to around like 3 seconds for block time, which is pretty good.
Okay. So that makes sense. So in general, like since we are now on the relay chain topic, right? Like, can we talk a little bit about? You mentioned like 12 seconds on the parachain and 6 seconds on the relay chain, right? Like but can we go get a little in detail regarding like how Babe, like what is the role of Babe there? What is the role of Grandpa there?
Yeah, good point.
Yeah.
So Babe is block production, and this basically randomly selects which validator will be create the new block. This doesn't mean the block is finalized or correct yet. It just means the block is created. And we fill this block, with a bunch of state transitions. And then Grandpa is the finality gadget, which if you're familiar with the concept of finality, it essentially, you cannot roll back that change in the blockchain when something's finalized. Bitcoin, you have probabilistic finality, which is like after 6 blocks or so, the transaction will be finalized and you're sure that it's a legit change. Versus some other protocols, I think, does Ethereum have absolute finality, if I'm correct? Or is it still probabilistic? It's subjective, right?
Yeah.
Okay, yeah, it's a little different, I think, in Ethereum. But in Polkadot, it's absolute. So once Grandpa says it's good, it's good. And Grandpa is actually quite complex. It involves like querying the states or validators all coming together, and finalizing takes a little bit more time. But once it's finalized, it's done. It's like instant. But to gather the information for Grandpa finality takes some time. But yeah, so Babe, first you make the block, right? You make the block, and then you fill that block with state transitions with Grandpa. And once it's finalized, then you can be sure that the state transitions from all these different parachains are finalized with Grandpa.
Okay, makes sense. So typically, as we have seen with our tests on our testing and testnet with Avail, for example, right? Like, so generally, blocks get finalized pretty quickly.
Yeah.
But are there scenarios where it might take more time? When can that happen? Why does it happen?
Yeah, so there's, again, Grandpa is actually quite an involved protocol. Like, it's we can probably spend an entire whiteboard just talking about it. But basically, different validators will kind of propose. So you have like validator 1, validator 2, validator 3 will kind of propose, their history of blocks. Like, hey, I have up until block 5. I have up until, maybe I have block 6 already. I'm up to block 4. So you have to kind of like converge and agree on what's the finalized state. Was block 6 legit? Was the block injected at block 4, matching the other validators? Is there some discrepancy? And this uses, like kind of BFT style consensus. If we have 2/3 plus 1, I think even, then we're actually able to, come to consensus on the final version of the blockchain. But, and those dishonest actors, which maybe you can see clearly, of course, there's some cases where like, you may just accidentally receive some data, and that's like not slashable, but you can be slashed if if you have multiple instances where you're just like including bad blocks on purpose. Like, it's like very obvious, right? Yeah. So in the cases like those, I'm not sure if it'll, take necessarily longer, but it does have to be worked out. Yeah, for sure.
Okay. And in general, from a very high level point of view, like the BAPE protocol is basically a random selection of one of the validators of the set, which does the block production.
Yes.
And in general, does Grandpa include the whole validator set, like 2x3 of the whole validator set? Or so when does that subset come into play, which you mentioned a while ago?
Oh, when the subset come into play?
Subset of, so you mentioned.
Oh, yeah. So these guys, these sub-validators, and maybe I should have explained that better. These guys make the block backable. So there's kind of 3 stages of a block. It can be a candidate, and then it can become backable, and then it becomes included. This is like the final stage, right? Mm-hmm. This is kind of the path, as you will. So candidate to backable to included. The candidate just has information that looks pretty good. Backable is the subset of validators say that this is backable for the whole set of validators. And then the included is when it's finalized by Grandpa.
Okay. And like, what is this subset of validators, right? Like, is it randomly chosen? How big is it? Roughly.
So I'm not sure roughly how big they are. I'm not sure exact. I think it's 16. I believe it's 16 validators selected per chain. But I think it can vary as well in size. But typically, I think that's around how much it is. But these are kind of selected and are able to validate these blocks and then make it backable, where they can then be included by the relay chain.
Okay, makes sense. Okay, so to recap, what we have actually now gone through is, like the entire architecture of the relay chain and the parachain, the Polkadot ecosystem. We have looked at what parachains, like how blocks are produced in parachains, how what data is being passed back down to the relay chain. And what happens on the relay chain itself, right? Like, I mean, how blocks are produced there, how parablocks are, termed as backable, then finalized, and so that is. And how many parachains are we talking about? Like, this construction can handle at the moment.
So at the moment, I believe the amount is 100 parachains.
100 parachains.
But with things like asynchronous back-and-coming, where you can kind of asynchronously prepare and finalize stuff, that can grow to much, much more. I don't know the exact amount, but I know it's going to be substantially many more parachains, or basically shards on the network. So.
Okay. Makes sense. So yeah, I mean, I think basically, can we talk a little bit about the parachain economics? How does that really work?
That's a good question. So parachains can choose their own separate economic model if they want to, depending on what they're doing. But of course, at the end of the day, they're deriving their economic security from Polkadot, right? The dot, dot will kind of secure these parachains economically, because dot is used, obviously the validators have stake and everything like that. It's a proof of stake system after all at the end of the day, or nominated proof of stake system. So DOT can kind of help secure all these different parachains where they don't need to worry about creating their own token and generating their own economic security, their own supply, and having their own validators, because they only need to supply collators to the network. They don't need to worry about managing a token necessarily, even though of course Parachains may choose to do so if they want to. At the end of the day, the stake of DOT or stake dots on the relay chain network accounts for the economic security for these parachains. As far as their own separate economic models, they can choose what to build for that. Like it's, they can entirely choose what to do for that in that case.
Okay. So this seems like a useful, like comparison between Polkadot and the Ethereum ecosystem, because rollups on Ethereum, for example, can choose their own economic incentives, right? Like, so most rollups today have run centralized sequences, but like most are looking towards, like some sort of decentralized sequencing where, like it could be POA, proof of stake, for example, or something.
Right. Yeah.
But ultimately, they derive security from Ethereum.
Yeah, there's also, I think, restaking too, which is pretty interesting. I was just looking into that. This kind of this is kind of, I want to say, a little bit more comparable to something like restaking, because the idea is like, well, how do you achieve a sense of decentralized trust, right? How can I just like jump onto this relay chain thing and just start validating that my information is correct? Or how can I know that this parachain is also being finalized? And it's kind of DOT gives you this sense of, like the notion of DOT, not like DOT itself, but all these processes. At the end of the day, you produce these blocks which represent like trust, basically, like it's trust free. You already know that you can trust this block, no problem, because of all these different proofs that go into validating it. So, and obviously those incentives and the token, and the economics of it, economic security, kind of achieves that.
Okay, makes sense. I think this is clear. Shall we now move to communication between the ecosystem, parachains, for example, or between the relations?
Yeah, so of course, I guess you can call it like a perk almost of when you're a parachain, you have access to this really cool protocol called XCM. And XCM stands for Cross Consensus Messaging. So XCM is the idea that you can kind of convey your intention of what you want to do on one consensus system to another consensus system. When I say consensus system, I mean something like a parachain or something that's like under this body of consensus, right? Because this is like, ensuring that all these different things have consensus. So XCM allows us to communicate between these different shards. It's cross-chain consensus. Or cross-consensus messaging, So cross-consensus messaging lets us send these like very arbitrary or generic messages that may do things like natively, like, hey, I want to transfer my parachain's like native asset to DOT, or even to another parachain. And it's worth noting that this is the format of the messaging. So this is a message format, not really a transport method, right? There's different ways to currently to send these messages to different parachains. One of them, the main kind of like one, is called XCMP, and cross consensus message passing. This one is currently being developed because ideally you want to communicate directly parachain to parachain, but what's kind of used right now is HRMP. And HRMP, it was just horizontal message passing. HRMP, horizontal message passing. This lets you kind of go through the relay chain first and then down to the parachain.
Okay.
So it's important to differentiate that XCM, which just gives you basically this format for sending messages, is the format, and these are like the transport layers, right? And getting more into the XCM format, you can think of it a little more as like a set of almost like CPU instructions, right? So you have like this kind of, it's called the XMVM. It's not really like a virtual machine, but they call it XMVM. And it's able to accept a series of instructions and then kind of hop through the various parachains and execute those instructions in order.
Okay.
So I can go on like start from parachain A and execute something in parachain B, then parachain C, and get some results from that.
Okay. And so how does this really work under the hood, right? Like, I mean, in the sense that, is this cross-chain messaging, like, I'm assuming there has to be some, messaging inbox, outbox being maintained along with, like when the parachain is sending, its message, its block back to the relay chain, right? Like, I mean, along with the, let's say the state root, for example, right? Like, is additional some information being sent for XCMP?
That's a good question. So for XCM, there's nothing like when you send a message using XCM, it's not like being included within the block, not the para block, right? All you're doing is you're sending an instruction to be executed on that destination parachain.
Okay.
Right? So if I'm parachain A, right, and I send some instruction to mint some asset, right?
Yeah.
So there's like some mint instruction to parachain B, right? It's not going to execute any state changes on parachain A. All I'm saying is, hey, I'm from parachain A and I want to mint something on parachain B, right? So the state change is going to occur on parachain B, right? It's not going to occur on parachain A.
Okay. Yeah, but I mean, what I'm trying to get at is, like, how does B know whether the message from A, is coming from A?
Good question. So there's this concept of it's called a multi-location, and basically this multi-location specifies like the junctions, they're called, or the hops needed to get to that specific parachain. So I might say like, from parachain A, I might want to go to parachain B, where I might want to mint something to some account A, right, on parachain B. And then, so this would be like a series of junctions which end up being this multi-location, and this basically sends that message with this multi-location to parachain B saying, here's a series of steps I want to execute. And then parachain B can look at those steps and say, does this match with my XCM configuration? Do I want to allow these messages? And then it will execute these state changes accordingly if it's okay.
Okay, so no, can you repeat that again? Like, where is this multi-location being?
So when you send something from a message from parachain A, like part of your message, of course, or basically what your message is these series of instructions, right? Yeah. But these series of instructions need to know where to be executed. Right. So each one it specifies this kind of path or multiple hops.
No, so but where is this maintained? Is it maintained on the relay chain? Like,
no, so each parachain can choose to support XCM.
Okay.
There's something called the XCM executor, which is responsible for this stuff, right? And you can think of it kind of like almost like a CPU in a way. Like, you send this instruction, is it valid? And each of these has like some like config, so you can configure this to only accept like certain kind of messages if you want to, something like that, and ensure that this state change even wants to be or should be executed on your parachain. This kind of takes care of that.
Okay, so I think the main question I'm trying to maybe ask is, like, how do you authenticate like these requests, like whether it is coming like from, like, because on A, as I understand, like on the parachain, as I understand, like this is like a trusted set of, like, you don't basically need a trusted party in that sense. Like, I mean, of course there are some parties that run the parachain, right? Like, I mean, how do you ensure this came from A but not from C, for example? Like, or can C spoof like the message?
That's a good question. So what, like, for example, what currently needs to happen between various parachains is like they kind of need to trust each other in a way because of this problem, right? that you don't want to just receive like random messages from Parachains or just being like flooded, right? Obviously, like in a realistic sense from the engineering perspective, it has like a queue of messages and all this stuff. That queue can get like full. You don't want that happening. So usually you have to establish like a channel between them, or this, that goes through like right now HRMP, which goes through the relay chain down to another parachain. You have to establish that channel that you actually trust this parachain's interactions. And of course it knows, where it came from, like the destination and the origin of this message. So, you can only accept messages from like verified sources which you want to include. And that's like within your configuration. Like you can choose, I want to accept from parachain A, B, and C because I trust them, but not, parachain D or F or whatever, or something like that. Yeah, XCM is known to be not confusing, but it's a quite abstract thing because it's so generic and generalized that you can configure it like pretty much however you want, which is really good because you can have very instructions very specific to your ecosystem, but it also means that you need to make sure that other parachains can also interpret it. And of course, that's part of its job is to do that.
Okay, makes sense. Okay, so then let us just step back from the architecture a bit, right? Like, and then talk about a little bit about like parachains, right? Like, what are the kind of parachains available? What are people doing on them, right? Like, I mean, we've heard of EVM parachains, but also like other general parachains, public good parachains. There's something called Asset Hub, Bridge Hub. So you can just go through the landscape a bit.
Yeah, so zooming out a little bit, so we just dove into a bunch of architecture, and just to recap, essentially, the role of the relay chain to the parachains is to give them the sense of economic security, so they don't have to worry about managing their own token, allow them to communicate with one another in some trustless environments. But yeah, like what are they actually doing, right? Why would people even want to create a parachain in the first place? There's a number of applications right now. So some teams have chosen to build, obviously in Polkadot, teams like Moonbeam and Akala. Moonbeam takes, for example, they actually implemented an EVM within their Substrate runtime or within their Parachains runtime. So they're actually able to like execute Solidity smart contracts, right? So you can actually like run a parachain that runs EVM on there. And of course, this has numerous benefits. You can also, from here, connect to like Ethereum mainnet if you want to, something like that. So it's quite cool in terms of interoperability. And then, of course, like you mentioned, Bridge Hub, Asset Hub, and these different things. This is actually a newer effort and further into the eventual like desired architecture of Polkadot, which is to further shard these processes. Ideally, the relay chain's main thing would be just to validate parachain blocks. That's all it should be doing. Right now, the relay chain also takes care of like staking, right? Staking, balances, like thought balances, amongst other things, right? Governance, like OpenGov, all these different responsibilities the relay chain has. Eventually, what you want to do is to have various system, now they're calling them system parachains because you said common good parachains. Actually, recently they're more favoring the terminology system parachains, right? Okay. Because these are like, you can think of them like, kind of like on your computer, you have these core processes that run, right? And they run like this multi-threaded environment. Similar thinking here. You want to have, these things as their own separate cores where they then talk to the relay chain as parachains.
Yeah.
Right? And of course, subsequently, then these can also talk to other parachains in the ecosystem.
Okay.
So, yeah.
Okay, makes sense. In general, what is the rough mix between let's say general purpose chains on parachains and app specific chains, right? Like, do you see like a pattern there in the Polkadot ecosystem?
That's a very good question. Currently, there are a few like app specific ones. For example, there's parachains like Kilt, which just do identity, General purpose, there's a couple of smart contract chains. I guess you can say those are more general purpose because they support like a multitude of smart contract platforms. Chains like Astar, they do things like they have an EVM palette so you can do Solidity. Then they have an ink palette so you can do like WASM contracts of all kinds of different things. Those are more general purpose. I think ideally on Polkadot, what we would like to see are more app specific. Like the goal is so you can get on Polkadot, build your thing to exactly what you need it to. It's optimized exactly for your use case, and everything else should be taken care of. Economic security, backing by all this, relay, by the relay chain, by these validity and availability checks, all that should be taken care of for you. You should just focus on your app specific logic. But as far as like available right now, there's quite a few doing more like general stuff and more like DeFi oriented.
Mm-hmm. Okay.
Yeah.
Okay.
A few data aggregation solutions too, like publishing data feeds or access to various storage solutions. That's also happening. Yeah.
Okay. Makes sense. Okay. So in general, like to the economic security bit, right? Like, I mean, in general, how much DOT is staked currently, roughly? Like, what is the economic security of Polkadot looking like at the moment? And I've just taken a look at like Kusama, which is the canary chain for Polkadot, and so like there are like 297 validators on Polkadot currently and 1000 validators on Kusama, right? Like, yeah. And I think Grandpa Web consensus can eventually support up to 1000 validators, maybe more. So what is the target there? Why is it lower on Polkadot at the moment? So what are some of the concerns there?
Yeah, that's actually a good question. I don't have like specifics on the ideal number of validators or ideal. I think it's actually at a pretty healthy state. I believe the ideal amount staked, and it changes, is around 75%.
Okay.
And I think typically it's maybe around more like 50-ish%, 40 to 50%.
Mm-hmm.
I can't speak. I don't like remember all the networks. That's off the top of my head right now.
Yeah, no problem.
But yeah, it's a good question though. Obviously, it depends on the validators to be interested to stake,
mm-hmm.
right? And that comes with usage of the protocol and things like that. So
cool.
Yeah.
Okay, makes sense. Okay, so I think so we've gone through the architecture, we've gone through the relay chain, parachain, economic subbit, parachain landscape a little bit, cross-chain messaging. You explained XCMP, HRMP a little bit. In general, do you want to talk a little bit about the improvements that are coming soon to Polkadot? Like I think there's something called core time, I guess.
Yeah. So the idea kind of been, excuse me, because the details are still a little bit sparse on it. It's pretty covered at like a high level. The idea with core time is like, well, before when you want to have a parachain, you go through this process of getting like a crowd loan. Like so you get like basically like you raise funds from people in the relay chain network, and then you auction it. And then you go through this auction where you compete for your parachain slots, right? And then if that's successful, then you get your parachain. But this is gonna, I think, kind of move more away to a more like elastic or like dynamic way of allocating blocks, because you may go through all this trouble, become a parachain, and then your blocks may be empty. Maybe your parachain's not even being used, and it's quite a bit to bootstrap a team in a blockchain and kind of arrange all of that. So the idea is, you can eventually you want to only pay for the blocks that you use. So the blocks, as soon as you have some data, you only kind of pay for that, and that's it. Especially in terms of the relay chain network, right? Really, what use is it if you're just validating empty blocks all the time? It's not really that great. So the idea is you can have like this elastic capability. And that's where kind of, instead of saying like parachain slots, as they're often referred to, it's more like their cores, right? So their cores and part of this kind of multi-threaded distributed state machine, like amalgamation thing, right? So they're all working together as cores. And I think the idea is you can kind of buy amounts of core time, right? For how long your core should live or something similar. But yeah.
Okay. Any other future upgrades that you are excited about that you want to kind of just point out quickly?
Yeah, I think I talked about it briefly. Asynchronous backing I'm looking forward to, because it basically will allow some of these upgrades to happen. Basically allow blocks to just kind of be built in the background and then included and backed when like they're kind of ready. So instead of things having to happen within like this 6-second window or this 12-second window, it can kind of take its time and be included when it has to, when it's kind of ready to. And I think that's very, very huge, especially in terms of parachain validation times and relay chain validation times, and also elastic scaling, which is this concept of like only paying for what you use for versus intimidating it. You either like build a contract or build a blockchain. Now you can kind of build something in between with your own custom logic, but it's powerful enough to have the implications of an entire blockchain ecosystem.
Okay. Makes sense.
Yeah.
Okay, so that's cool. I think maybe we can talk a bit about Substrate, the framework itself, because we use Substrate in Avail. So it's the dominant framework that is used in the entire Polkadot ecosystem. So maybe some thoughts around Substrate.
Yeah. So everything I mentioned here and so far, like you can kind of think about it like this. This is Substrate. Like everything here is built using Substrate. And of course, like the word substrate means to provide like a foundation for something, and Substrate gives you that foundation for all this stuff, right? So these changes, these scaling changes I mentioned, the proof of validity stuff that I mentioned, it's all in Substrate. And Substrate is basically a blockchain framework, for those who don't know, a blockchain framework to build blockchains, right? Similar to how something like React, like you build websites. I use this example like very loosely, but Substrate gives you a strict set of methods and tools and building blocks to build your chain, essentially from scratch. So things like networking are taken care of, fork resolution mechanisms, consensus, all these things which are usually hard to do and you need a lot of people to do. Now you only focus on the parts which matter, which is really the business logic. Most people just want to worry about business logic. So that's what Substrate does essentially. And it facilitates all of this.
Absolutely. Yeah, we also found Substrate to be pretty good to work with in general, and so we don't have to reinvent the wheel on all parts of the stack. And Substrate is beginning to be used outside the Polkadot ecosystem as well. So if you see, Avail is using it, but Madara from Starkware is also using Substrate, and we've seen a variety of other teams starting to use it. Little bit similar to how Tendermint was used outside of the Cosmos ecosystem, and so Substrate is also getting that reputation.
Yeah, no, exactly. And kind of the cool thing with Substrate really is this, like you said, it's not like Polkadot specific. I mean, obviously many parts of it can be like, kind of tailored to Polkadot because that's what it's used for. But kind of, it's a general library and like protocol which you can use to build something entirely different if you want to, right? Some people, there's actually a few in the Polkadot ecosystem that aren't parachains. They just built their solo chains to do like, very specific things. For example, there's a chain called Aleph Zero, and they have a protocol which achieves like sub-second finality, like really fast finality. It doesn't use ground it uses something else that's like super, super fast, like it blocks, just like you should see them populate on the screen. It's like really, really fast. So they're able to do that. Obviously, I guess you can call it like a limitation. When you're with the relay chain, you have to kind of follow the relay chain. And then, it's not slow. It's not sub-second or whatever. So, they choose to run their own solo chain, and they do that with Substrate, and they're able to create their own consensus model and everything using Substrate and those different toolings.
Yeah. No, Substrate is pretty good. In general, I think basically since we have now talked about like this whole the relay chain, parachain kind of a ecosystem, right? I just want to draw up some parallels to the Ethereum rollup ecosystem, where there is an Ethereum base layer and a lot of rollups on top. So like how do you think about like this as a contrast in how these ecosystems are tackling scaling challenges?
Yeah, so it's quite interesting, right? So Ethereum, I guess, and people already know this, like Ethereum is general purpose, right? It's like essentially like a large global state machine. That's kind of its goal, right? And you can execute things on top of this state machine, various contracts. But unfortunately, because it's so general purpose, it's not suited to like a particular thing.
Mm-hmm.
So rollups, come in to do that, which is why you need this second layer, this like L2 layer, right? L2, and this is L1. And it's this, of course, we kind of already know a little bit. I'll just give a brief synopsis on, L2s. They just take a bunch of state transitions, package them up, send them up, to the layer 1. And usually, there's different methods, right? So you can have optimistic rollups, and these just like assume that every state transition is valid, like automatically. And I know there's like a dispute and fraud resolution mechanism. Like if there's also like a challenge period, right? So there's an amount of time in an optimistic rollup where you can kind of challenge a set of state transitions, say like, hey, that doesn't look quite right. I want to challenge this assumption. Yeah. And the problem is that this can be a little slow, that like challenge period, right? But like a good thing is that you can also hold quite a bit of data, I think, inside of optimistic rollups. Right, and I think generally they're a little bit more flexible. Of course, then another big one in the ecosystem, ZK rollups, which everyone loves to talk about. ZK, of course, is nice because you just generate a single proof that just verifies everything for you at a very high level. That's what it does.
Yeah.
And of course, privacy preserving and all these other benefits. The problem with it is that building a general solution ZK like circuit is quite tough, as I understand it. I'm not a cryptographer, so I wouldn't really know, but building like a general solution to, for example, like on EVM, as I understand, is pretty tough as it stands. Another thing is the computation needed to run the circuit is also
pretty big.
Pretty big, right? It's a large amount of data.
Yeah, but I mean, just to inform, in general, now we have like 2-3 different big ZK EVM.
I think this is changing though. This is starting to change, which is very fascinating to me.
So like ZK Sync released their ZK EVM, Polygon released their ZK EVM. And Starkware already has like a Cairo VM. So basically, now things are already on production on the ZK side.
Yeah, no, that's actually awesome. I think one of the bigger problems with rollups in general, and this is just fundamentally like how they work, is that they can rely on this set of sequencers, right? And people have concerns of whether these sequencers can be centralized or something similar to that nature, So that's kind of a concern about L2s on that side of things. Versus if we kind of compare and contrast how layer 2s work, because layer 2s can kind of, as long as they end up getting into the format that the layer 1 likes, doesn't really matter too much what they do. Whereas like the Parachains protocol and Polkadot is very specific, right? We saw it's like a very involved process of like, it has to go through this phase, and this phase, and this phase, and then eventually it's included.
Yeah.
And that's like natively part of the protocol. It's for this reason that Polkadot is actually like considered like a layer 0, because it's like provides the most base layer of things for other blockchains to to finalize themselves on or to talk to.
Yeah.
But yeah, the Parachain protocol, in a way, it can be thought almost, it's a little bit more similar to like an optimistic rollup in a way, because, not quite, but if you want to kind of compare or think of it like that, I think it's a pretty fair assumption to say that, because there is the concept as well of, some fraud proofs and stuff as well within that process. So it's similar in that regard. But it's different in that you don't need to have like different sequencers or different a subset of things to run it. Obviously, you just have the validators that are already within the Polkadot network that take care of it for you. So you don't really need to worry about running a separate L2. Another thing is because of the abstraction of like the WASM packages and the proof of validity functions and stuff, this stuff is like very abstract, It's pertaining to that specific parachain. we don't need to worry about creating a general purpose solution because, you know, the parachain gives us that information already.
Yeah.
So in that case, it's quite useful. Just like, okay, this proof of validity function, set of changes, checks out, works, okay, nice. And then that subset of validators, you know, they scramble and there's another subset selected and they verify another parachain and so on. So I think that's kind of the main differences here.
Yeah.
Yeah.
Yeah, no, I mean, so I mean, I'm just trying to just see because, you know, like what I find is interesting is when Polkadot began its journey from, you know, like I think it's around 2017, 18, I guess. And so, so at that time, Ethereum didn't have like a roll-up strategy at that point in time, right? Like, so Ethereum was just one single layer. So we were trying different plasma scaling approaches and all.
I remember that.
But in general, you know, so Polkadot began that time with this relay chain, parachain kind of a thing. But it is very exciting to see, you know, like Ethereum also kind of moving in that direction, because now Ethereum is trying to become or, you know, like aiming to become a data availability focused blockchain, and you know, like it'll you know, like push execution to the layer on top, which is kind of like, you know, like not of course similar, but like in the sense that, you know, like there are similar dynamics at play, similar mechanics at play.
Yeah, I think it's important because people are starting to realize, and actually I have to say, just at Parachains, Sean from Polkadot Labs, he touched on this really important concept, which is like when most blockchains look for scalability, they're actually looking for interoperability, right? The ability for all these different layers to orchestrate and talk to one another. That's like the key thing. That's really what they want to do. Because once you can do that, then you can start passing data from one another, verifying each other in this way, which is more decoupled and not, you know, one big chain. Now you can separate that chain into a bunch of smaller pieces, which is way more efficient, which is what Polkadot tries to do.
Yeah.
But yeah, I find it interesting that Ethereum is catered more to this roll-up centric kind of future, which I find very fascinating, and I'm looking forward to seeing how this pans out. Obviously, it's nice because then you have complete freedom in your layer 2, right? But then this also could be a double-edged sword where you have complete freedom in your layer 2. So, you know, but yeah. No, it's actually, it's a very fascinating topic, how they're kind of, as I understand, Ethereum actually wanted to go to a more sharded system.
Yeah, initially that was the plan, that initially there was a execution sharding kind of a roadmap, but because of limitations of that approach, so they shelved that. So, you know, there was actually a two-part sharding roadmap. So there is a data availability sharding roadmap and execution sharding roadmap. But then they shelved the execution sharding roadmap, and now there's only a data availability scaling roadmap, so which is more roll-up centric. So roll-ups will handle execution, and, you know, like the base layer will handle data availability.
Right. Yeah, that's fascinating. I think if you want to like do the main contrast between Parachain protocol and then like ZK and optimistic rollups and this thing, the main thing is that this stuff is kind of like already baked in, more or less, right?
Yeah.
You know?
Yeah. So I think the main thing that I also like last month when I went to the Polkadot conference was, you know, like so one thing struck me was that what is happening on Polkadot is a more opinionated kind of development. Like so there's like a structure to which you need to adhere to enter the ecosystem.
Yeah, exactly.
And the one on Ethereum is more unopinionated, like it's more like a blank canvas, and so here it is very much homogeneous on, you know, like a lot of things like gel well, because, you know, like it's same consensus, and, you know, like there's protocols in place. In Ethereum it's more like a wild west, so you'll have a optimistic rollup and a ZK rollup and a ZK rollup, like there will be 5 different proving systems, and, you know, so it's much difficult to then interoperate in that sense, but, you know, like hopefully like a shared DA layer will, you know, like provide more interoperability opportunities, etc. And then, you know, like there are recent advances in ZK systems, which like recursive proving systems, which, you know, allow you to verify like a circuit within a circuit itself. And so, I mean, that is
huge,
also the context in which, like we are building Avail, in the sense that we believe that, like the base layer for rollups on top will need to be a data availability focused layer, right? Like, I mean, it has to focus exclusively on scaling data availability, because rollups need that to scale.
Yeah, exactly, because you need to be able, at the end of the day, to retrieve, these proofs or these headers in a way, that's, sometimes they can kind of be lost. I don't know what various sequencers will end up doing with this data. Every protocol, every L2 is different. So that layer of data availability is also obviously super important to actually have in place.
Absolutely, absolutely. Okay, I think this has been pretty informative in general, and I mean, Bader, any last thoughts you want to, or anything you want to add to this?
Not really. We really ran through like a lot of concepts. Like there's a lot of concepts, obviously, and I could have dived into maybe each one and done something. So I tried to go a little bit, try to cover everything.
Yeah.
But I think it's important just to realize that as it may be a little bit opinionated to like initially be within the relay chain's context, actually building your parachain or building like your runtime, you can do whatever you want with it. And I think that's a pretty important thing to also kind of take away from here. You're in complete control of your own application logic and your own kind of the way your protocol works. You're just getting the benefits from the relay chain in terms of finality and economic security and consensus.
No, I think that makes sense. Like it broadly falls in that, like from a very general Web 2 kind of a background, right? Like so when developers use systems today, like the cloud, for example, or like serverless systems, etc. Right? Like so, I mean, they don't focus on the networking behind that, or like nothing like that. Like they just bring their app logic, their data model, and like start building apps.
Yeah,
right?
exactly.
And so we are at that stage of the blockchain evolution that like developers have to be aware of the gory internals of what is happening, like behind.
Of course,
the infrastructure. And I think basically both ecosystems, like when Polkadot specifically are also moving to a place where like eventually all of this will be pretty abstracted away.
Yeah, pretty much.
And, like no one needs to like think about running validators or such, right? Like
yeah.
So just bring your app logic and data model, and like. But of course, this is a more trust minimized compute environment that we are bringing rather than like compared to Web 2.
Yeah, of course. Yeah, I guess you can say like Web 2 brought us a lot of UX. Things look really nice, but we don't exactly know what happens to data, where it goes, and how it's being verified, who it came from. Exactly. So this gives us the systems, across not just Polkadot, all blockchains really, right? We're not saying one particular chain is like the solution to everything. I think each one has a place within the ecosystem, which is why we're trying to bridge these things and bring these things together, because ultimately, it'll bring a lot more value that way. So,
absolutely. Yeah. Absolutely. Okay. Yeah. Thanks, Bader. Thanks for taking the time out. Like spending, and this session was pretty informative for me as well, and hopefully for the audience as well. And like again, thank you.
Of course. Thank you, guys.
Okay.
You want to ask the closing question?
Okay. Yeah. So so this is this is a question that like we try to ask at the end of the session. It's in the sense that like do your parents know what you do in at work, for example, or how do you explain what you do to your parents or like anyone close to you?
Yeah, so I'm lucky that my dad knows what blockchain is. Maybe my mom not so much, but I think they have a pretty good idea. Outside of that, the question I got asked before I came here is, wait, what exactly is your job? And I couldn't. I just say that I work, in distributed computing. I think that's like probably one of the best answers, is explaining, when you say blockchain, people think, oh, Bitcoin, oh, like cryptocurrency gambling. Like this is what people's minds immediately go to. But no, I think like the way I try to always explain blockchain is specifically is, it's a way to back data, give data some sort of integrity. And that's kind of how I would explain it, but yeah.
Yeah, it's a tough job, like basically explaining what we do or what we do to people.
Yeah, it has a lot of bad associations.
Yeah.
Like here, like this technology is pretty amazing all
Yeah.
across the board, but
Yeah.
Who was it that I think said? He said that I think there's only room in the world for only 5 computers. Someone said that.
Yeah,
I forgot the person who said that quote, but it's a kind of a
I think
similar.
it's the
thing.
IBM chairman or someone like that.
Yeah, I think so. So.
Yeah. That's true.
Yeah.
Yeah, cool. Thank you, Bader again.
Yeah, of course. No, it was fun.
Yeah.
Hopefully, I didn't like throw too much information because I
No,
know it was
no.
a lot, and it was like back here, back there, but it kind of does work like that.
Yeah,
Like,
yeah.